Hello, everyone. We are going to continue today with Unit 2, and we're going to move into Section 2, which is all about the periodic table. All right, so we're going to start with elements and compounds and review this real quick. We said elements were the simplest form of matter. There's about 114 known elements, and of which out of those 114, 92 are naturally occurring, which means there are some other elements that can actually be made in the lab, but are not going to occur on Earth naturally. Let's put it that way. All right, so you also have compounds, and compounds are going to consist of two or more elements that are chemically combined. These compounds can be broken down back into their, component elements, and the compound's properties, their physical properties, chemical properties, are actually a lot different from the elements that make them up. For example, the best one I can give you is sodium chloride, which is table salt. So you sprinkle sodium chloride on your food and you eat it and everything's fine. But if you were to break sodium chloride down into its sodium component and its chlorine component, and you try to eat sodium or you try to eat chlorine, you won't die. So you can see how putting together elements and creating compounds can totally change the properties of those elements. All right, so this next big section of this part of the notes has to do with the history of the contributions of several scientists towards the field of chemistry. So let's start with Democritus, who was way back in the day, 460 to 370 BC. Of course, back then, you're not going to have microscopes, you're not going to have any kind of machinery, technology, or anything to be able, you couldn't even see cells back then. But he had the idea that everything was made of invisible parts, and he believed that those small parts could not be destroyed. He actually coined the term atomos, which, of course, is the origin of the word atom. So he had the idea. He was very smart, even though he couldn't see any of this stuff. All right, much later, you have John Dalton. He is pretty important to this whole atomic theory thing. And we're now up to 1766. He proposed pretty much the same idea that all matter was composed of atoms, and they were indivisible and indestructible building blocks of matter. He proposed that all atoms of an element were identical, and so, this atom of oxygen is the same as this atom of oxygen. That's what he believed. And that different elements of atoms came in different sizes and masses, which is, if you look at the periodic table, you'll see it is arranged by the atomic number. And when you look at the atomic masses, for the most part, they're increasing as you move down the periodic table, showing you that, each element can be different sizes. All right, so John Dalton had an atomic theory. And what did this atomic theory say? Basically, that elements are made of atoms. Atoms of a particular element are the same. Atoms cannot be destroyed. Elements can combine in whole number ratios. We talked about that in the section 1 of Unit 2, where we looked at like C6H12O6 and H2O. So those particular, compounds were created by elements in particular ratios. And then chemical reactions are just when you recombine atoms. So we talked a little bit about chemical reactions, breaking apart this item to create this item, taking these elements apart, putting them back together again. Those are chemical reactions that form different, compounds. All right, so our next scientist on the list is J.J. Thomson. He's a little bit later, 1856 to 1940. He was a physicist, won the Nobel Prize, and he is famous for his cathode ray experiment. Now, this is a little machine that he put together. Here's a picture of it. You have the cathode end, which is the negative end. You have the anode end, which is the positive end. You can see here. You have a positively charged plate, negatively charged plate. You've got some power running through it. And back up a little bit, but basically this was produced in a vacuum, which means all the air was sucked out. He's running electricity through it, and he found the results of this cathode ray experiment. He found that there were some lighter negatively charged particles. Well, at the time, he wasn't too sure about, that they were electrons, but he knew that they were there, and he just called them cathode ray particles, which, of course, now we know are electrons. And you can kind of see how he's shooting the electricity through. And as these electrons are coming, they're going for that positively charged plate because, opposites attract. So the negatively charged electrons are moving towards the positively charged plate, not the negatively charged plate. Because, negative and negative is not going to attract, but negative to positive does. All right, so he discovered, he determined that atoms have a negative component and that there's an extremely large charge to mass ratio. We already said that they're very light in mass. The electrons are, but they have, a rather strong negative charge. And he created his own atomic model that is called the plum pudding model. Now, and he was British, so the British called plums, they called raisins plums. So basically, when we're talking about this is like a bread kind of thing that had raisins running all through it. So here is his plum pudding model of the atom. So you can see he thought that all this space here was positively charged, but you have all these negatively charged particles scattered throughout the entire atom, which now we know is not true, but he was getting closer to the true model. Okay, so that's why they call it plum pudding. It's just because, the pudding dessert with the raisins in it, and the raisins are the electrons kind of scattered throughout. All right, our next guy is Ernest Rutherford, 1837 to 1937, about the same time period. He was a British physicist. He discovered half-life, won a Nobel Prize for it, and he also did some work with radiation. We're going to talk about alpha and beta decay and types of radiation in section 4 of these notes. But he was trying to, look at Thomson's plum pudding model, which, does not have a nucleus. That model did not. And Rutherford did his famous gold foil experiment, which involved using a very thin sheet of gold foil that he shot alpha particles at. Now, your alpha particles are going to be positively charged particles. And what he noticed as he was shooting them through an atom, there's two pictures showing, they were being deflected. Okay, and really what was going on is they're being deflected from the center of the atom. So since the alpha particles have a positive charge, you know that the protons are in the center of the atom, which also have a positive charge. So those are like charges. They are going to repel each other. So that's the way he figured out that the center of the atom was positively charged, and that the first idea of there being a nucleus. Here's another picture kind of showing you his gold foil experiment, where he figured out that the atom is mostly empty space. The empty space part is, where the electrons are orbiting, and the nucleus itself is the most massive part. It's tiny, but it is the most dense part of the atom. Okay, that's your nucleus, and it's positively charged because that's where the proteins are housed. So this is where we get Rutherford's proposed atomic model, okay, which is going to have the nucleus. It's going to have the protons inside the nucleus, which are positively charged, and most of the mass is found in the nucleus, where you have the lighter, negatively charged electrons orbiting outside. Okay, so here's Rutherford's atomic model: electrons, protons. This is a helium atom just showing, but now we're seeing that you have the electrons orbiting around this very tiny, but it has most of the mass of the atom in the nucleus. Yeah, you can see here where the mass of the electron is 1/2000th of the mass of a proton. So when we say the nucleus is massive, I know it's a tiny, tiny little structure, but compared to the electrons, it is pretty massive. All right, you have Niels Bohr, 1885 to 1962. He was also a physicist. He studied with Rutherford. He came up with the idea that electrons are held in energy levels that are certain distances from the nucleus. So if you look here at our atom and the little dark, circles here. These are all your electrons. The blue in the middle is the nucleus. But these separate rings are his different energy levels in an atom. He said that they are in orbits that are stable and stationary with energy associated within each. We will talk about those energy levels in a future unit, but right now, just realize that he came up with the idea that where the electrons are orbiting the nucleus, there's a specific energy level associated with these different orbits. The lowest energy is found in the smallest orbitals, okay, which would mean as you increasingly go out from the nucleus, the energy in the outer orbitals are going to increase. And you can see in the numbers here, x, 2x, 3x, as you move out. All right, Robert Millikin, he was an American physicist, and he found the charge mass of an electron using his oil drop experiment. For now, just kind of know that, I know we talked about our other discovery where the electron, where J.J. Thomson found that the electron was very light subatomic particle, but he didn't know how light. So this guy came in and just did a more specific experiment to actually figure out the charge and mass of an electron. All right, we got a little bit more history here on quantum theory. Now, quantum theory is a theoretical basis for modern physics. Physics and chemistry go hand in hand for a lot of the topics. So this explains the nature and behavior of matter and energy on the atomic and subatomic level. And basically what you need to know from this is what I have in bold print here. The quantum theory tells us electrons exist as both waves and particles. So if you think waves as being, I guess the easiest way I could say is almost like light waves, but they can also exist as particles. It's really weird. Here's a couple of video links if you're interested in that kind of thing. You can, check this out. Quantum theory can be, pretty confusing to some people. To a lot of people, to most people. But anyway, I just put it in bold print here, which you kind of need to remember from that. All right, next we have Wolfgang Pauli, 1900 and 1958. He was Austrian. He was also a physicist, and he developed Pauli's exclusion principle, which we're going to come back to in a future unit. But that just states that two electrons cannot be in the same place at the same time. And again, we will review that or actually come back to it in a future unit. He also won the Nobel Prize for his work. All right, so now we have Dimitri Mendeleev. He was a Russian chemist and inventor, and it was his work that led to the organization of the periodic table, putting the elements into rows according to their atomic mass. Okay, then that's not how we have it now, but when he was putting it together, he put it together based on their atomic mass and into columns based on chemical and physical properties. So here's a little video. If you're interested, you could click on that to learn a little bit more about Mendeleev's periodic table. But we had Henry Moseley come in, and he was also a physicist, but he discovered that the major properties of an element are based on their atomic numbers, not mass, which again is the basis for how we organize the periodic table today. It's based on the atomic number and not the mass. All right, little checks for understanding here. Let me move my picture a little bit so y'all can see. If I can get it to move. Yeah, I guess it didn't do much good, but at least you can see the answers now. Okay, so here's the cathode ray tube. This is J.J. Thomson's work. And it says when English physicist J.J. Thomson was carrying out experiments on cathode rays, he was able to determine that the rays consisted of particles. He also called them corpuscles. We said that he called them cathode ray particles, but he also called them the corpuscles too. These particles were later named, and the answer is, hopefully you said letter B, electrons. All right, another checks for understanding. After 1911, most scientists accepted the theory that the nucleus of an atom was very dense and very small and had a positive charge. What led scientists to accept this theory? Was it that Dalton's theory of the atom was over 100 years old? That scientists before 1911 used the scientific method of inquiry improperly? That a new model proved that the quantum theory of the atom was inaccurate? Or was it because of Rutherford experiment with the alpha particles in the thin piece of gold foil? And the answer is, hopefully you said letter D, Rutherford's gold foil experiment. All right, this is the last one here on this page is which statement best describes the density of an atom's nucleus? The nucleus occupies most of the atom's volume but contains little of the mass. The nucleus occupies very little of the atom's volume and contains little of its mass. The nucleus contains most of the atom's volume and contains most of its mass, but the nucleus occupies very little of the atom's volume but contains most of its mass. Okay, you should have chose letter D, where the nucleus occupies very little of the atom's volume. Remember, we said it's very tiny in the middle, and that is very massive compared to your electrons, so it contains most of the atom's mass. So that was letter D. All right, you guys need to know subatomic particles. You're like, what is that? Well, you already know what they are. The subatomic particles means they are the parts of the atom. So you're talking about protons, electrons, and neutrons. And if you look at your table here, you're going to need to know this information, the symbols, because sometimes I will just write the symbols instead of writing out the words. So you need to know that P with little positive superscript means it's proton. Of course, that's the abbreviation for proton, and the positive symbol is telling you that proton is positively charged. Electrons are usually written as a lowercase e with a negative sign as their superscript, telling you that, hey, that's an electron and it is a negatively charged particle. And then neutrons are written with like a little zero as a superscript, and that's because they're named for what they are. They are neutral. They have no charge. Okay, so you can see the masses there. The proton is 1. The neutron is also about a 1. That's what that little squiggly line means. It means approximately. And then the electron is approximately 0. It's almost no mass at all. Okay, then you have your positive charge for the proton, negative charge for electron, and no charge for neutron. And then the locations, proton and the neutrons are found in the nucleus, and then the electrons are found orbiting the nucleus. And then you have your picture up there to get your visual. All right, we have our periodic table of the elements here and its layout. We will, of course, revisit the periodic table in almost every unit, but what you need to know now are the basics. So the rows, which are going across like this, row 2, row 3, row 4, those are referred to as periods. The columns that are going vertically, top bottom here, those have 2 names. You can either call them families or groups. Okay, the elements are arranged in an increasing nuclear charge, which means it's their atomic number. So that's how they are arranged, increasing. Here's the lowest atomic number, and here's 2 for helium, 3 for lithium, and so on and so forth. You read it by starting here and going across to helium, and then back over here to lithium, and you're moving across this way. You can see how the numbers are increasing, 5, 6, 7, 8, 9. Those are the atomic numbers. Okay, the nuclear charge is the charge of the nucleus of an atom based on the number of protons and electrons that are present in the atom. So as long as you have a stable neutral atom, this number that they're using to arrange the atomic number, that's actually the number of protons and the number of electrons. Again, in a stable atom, stable neutral atom. Same number of protons as the electrons, they cancel out. They don't have a charge. All right, the periodic table, you'll see the little boxes as you saw here, and if I give you one that's kind of blown up so you can see it, we're looking at calcium here. It's going to give you the element's name, calcium. It's going to give you an atomic number right here. It's going to give you an element symbol, and it's going to give you the atomic mass. Okay, atomic mass is bigger than your atomic number because the mass includes both the protons and the neutrons added together. All right, elements can be named for mythical concepts or characters, including astronomical objects. It could be, minerals, similar substances, a place or geographic region. They just get named sometimes, even for a scientist, whoever discovered it. So it's based on the English or Latin names. Example, lead is the symbol's Pb, and you're like, where the heck did they get Pb for lead? Well, that's Latin. Plumbum is lead in Latin, so some of the symbols come from not the English word. All right, so looking at the atomic number, that's the smaller number here, sometimes referred to as the letter Z if you're doing some kind of math, something with it, represents the number of protons. Remember, we said protons are written as a lowercase p with a positive charge. Also called the nuclear charge because, again, protons are found in the nucleus, so that they would make up the charge of the nucleus. Since each of the protons is equal to, remember we said it had a mass of +1, and if you have more pluses with charge, means you're going to have more electrons needed to neutralize it. So again, with neutral atoms, you're going to have the same number of protons as you do electrons. Okay, remember we said Z represents the nuclear charge, or the atomic number. So basically, in other words, the number of protons, sorry about that, down here, the number of, disappear. In other words, the number of protons equal the number of electrons in a neutral, stable atom. Now, we're going to talk about ions later, which are charged atoms. You should have talked about those in biology and possibly earth science. Right now, we're just talking about the stable, neutral, no charge atoms. Okay. So you're looking for number of protons, you look at the atomic number. You're looking for the number of electrons, you look at the atomic number. All right. Let's look at average atomic mass here real quick before I go into the isotopes. This is the bigger number, okay? And like I said, the reason why it's bigger is because it's including the proton count with the neutron count. So since atoms of an element can differ in mass due to varying isotopes, let's go back up here to isotopes. All right, what is an isotope? They are different versions of the same element. They have the same number of protons. They have the same number of electrons. The only thing that's different is the number of neutrons. So if you have a different number of neutrons, that's going to give you a different mass number. Okay. Again, right here it says this affects their atomic mass. Mass is equal to the number of protons and neutrons. All right, since atoms of an element can differ in mass due to varying isotopes, the atomic mass displayed on the periodic table is the average atomic mass of all known isotopes for that element. I know you probably heard of carbon-12. Okay, that's like carbon, the most popular and most naturally occurring one. But there's also carbon-14. Hopefully in earth science or biology, you talked about how carbon-14 is used to date like fossils and rocks and stuff. So carbon-14 is an isotope of carbon, which carbon-12 is as well. But carbon-14 is one that's not really, doesn't show up quite as much as carbon-12. Well, we'll talk more about that. But just know that there are different isotopes for every single element. And the ones that are on the periodic table are the ones that kind of show up the most. They give you the average atomic mass of all the possible isotopes. We're actually going to be calculating that soon, so in section 3. All right, here is a checks for understanding question. So here's a small portion of the periodic table. Okay, let me move my face out of the way so you can see the answers. The picture shows a small section of elements in the periodic table. Which element has one more proton than element X? Okay, so here's element X, and they want to know, is 1, 2, 3, or 4, which one has one more proton than this? Now, remember, I told you that the periodic table is set up based on atomic number, and atomic number tells you how many protons that element has. We also said as you move across in rows, when you get to the end, you start over on the next row and move this way, that's an increasing atomic number, which means increasing number of protons. Okay, so what do you think the answer is to this one? Hopefully you said letter J, which is element 4 here, because X would have an atomic number that is one larger than the element here, but number 4 would have an atomic number which tells you that there's one more proton than the one before it. Okay, because we're moving this way across the periodic table, and then when you get to the end, you start over and go over the next row, and again, increasing atomic numbers as you move across the rows, and atomic number is telling you how many protons there are in the nucleus. Consider any set of 3 adjacent elements in the periodic table. Okay, so 3 side-by-side elements on the periodic table. For which characteristic is the average for those three elements always equal to the value of the middle element. Okay, we basically just told you that the periodic table is set up based on, hopefully you said atomic number. So our answer for this is letter A, atomic number. All right, question down the bottom, why is cobalt placed before nickel on the periodic table of elements, even though it has a higher average atomic mass? Now, we just said that the periodic table is based on or set up with atomic numbers increasing as you go across the rows. We had mentioned Mendeleev had set up his based on atomic mass, but that's not how we do it anymore. Every now and then, your average atomic mass, well, you know, most of the time it will be increasing as you go because your elements or atoms are getting larger as you move across with the atomic numbers. But every once in a while, you'll have one that's not going to fall in line. Okay, the average atomic mass won't be increase; it might decrease, but the atomic number always does increase as you move across the periodic table. So, why is cobalt placed before nickel? It wasn't because cobalt was discovered first, and it wasn't, you know, because nickel has fewer electrons. It doesn't have anything to do with the density. It's letter A. Nickel has one more proton. Okay, so cobalt has one less proton than nickel does, or nickel has one more proton, however you want to say it. So your answer for that was letter A. A little more on isotopes. Okay, since each isotope's mass is different due to different numbers of neutrons in the nucleus, they are named based on their mass differences. Here's an example using hydrogen with three possible isotopes for hydrogen. Protium is hydrogen 1. It has one proton and no neutrons. Deuterium, which is written hydrogen 2, has one proton and one neutron. That's where you get the 2. And then tritium is hydrogen 3, which has one proton and 2 neutrons. Now, notice how the proton count did not change for any of those. Proton count stays the same for the isotopes. The only thing that changes is the neutron count. Okay, and you can see a visual for these down here. And here's your nucleus, only has one proton, one electron. Here's your nucleus here with one proton, one neutron, and you still have one electron. Remember the electrons, the number of electrons is going to be the same as the number of protons in a stable atom. And we haven't started talking about ions yet, so right now everything's neutral, everything's stable. And then for tritium here, you'll see the one proton and 2 neutrons. So you can see how the neutron count has changed with these three, which makes them different isotopes. Now you have to understand how the notation for writing out these elements. So you'll see that you're going to have the chemical symbol, and they just use X here, but we could have used, we talked about calcium earlier. This could be Ca for calcium. It could be Na for sodium. Okay, so this is where you put your symbol. Here we got hydrogen down here, so you can see that's the symbol on the periodic table for that element. Then you have a superscript and a subscript. Okay. The superscript is going to be your mass number, the larger number. Of course, remember the mass is the neutron plus the proton count. And then the subscript number, which is written as Z here, that's just telling you the number of protons. So here we got hydrogen showing you this. This is an isotope. This is the tritium isotope for hydrogen. So 3 is its atomic mass. And usually when you have isotopes like this, you're going to write when you're writing it out so people know which one you're talking about, you're going to put the name followed by the actual atomic mass number. So we know which one. So like carbon 14 or carbon 12, we know which isotope you're talking about. But when you write it out in symbol form, you'll do the same thing, but you're just using the symbol for the element. You put the atomic mass number here on the top. You put the proton or the atomic number down here in the subscript. All right, some checks for understanding. To see if you understand, I want to know how many protons, neutrons, and electrons are in each isotope. So I've only given you a little bit of information. All right, you would have to look on the periodic table for these. This is carbon 14. This is carbon 12. This is chlorine, and this is zinc. Do a little something in here we'll talk about in a second. But so if you look at the periodic table, let me share that screen with you real quick. Not sure if you can see that. I don't know if you can see it on here, but anyway, I'm looking at the periodic table. It says carbon has an atomic number of 6. Okay, so let me go back out. We're looking at this. Let me make this a little bigger. But so that your 6 would be down here. Okay, let's go to the next page. You would need to know the atomic numbers for these, which are the blank boxes. Okay, you can't see the boxes, but you're supposed to be putting that subscript atomic number down here, and then that way you can figure out the protons, neutrons, and electrons. So you would need your periodic table, and you would need to look up these symbols, and then you would need to get the atomic number and put it as your subscript. So I've done that for you here. I was afraid you may not be able to see the periodic table on this video, so I've already done it for you. So 6 is the atomic number for carbon-14, but 6 is also the atomic number for carbon-12. Remember we said in isotopes, the only thing that changes is the atomic mass, because the only thing that changes is the neutron number. Proton number stays the same. So how do we tell the number of protons? So the number of protons is the atomic number. Carbon-14 has 6 protons. And we also said that these were stable neutral atoms. So we said the number of protons is also equal to the number of electrons. So for carbon-14, it would have 6 protons, it would have 6 electrons. Now, how many neutrons do we have? The way you figure that is you take this atomic mass number here and you subtract the atomic number from it. Okay, so we're going to end up with, we already said 6 protons because it matches the atomic number. We also said 6 electrons because these are neutral stable atoms and the number of electrons equal the number of protons. And then to figure out the neutron count, all you do is subtract the atomic number from the atomic mass and we get 8. Now, on the other hand, if you're looking at carbon-12, same thing. Atomic number tells you the proton count, but it also tells you the electron count in a neutral stable atom. How do we figure out how many neutrons are there? You subtract the atomic number from the atomic mass. 12 minus 6 equals 6. So in the carbon-12 isotope, there's 6 of everything. All right, chlorine. 36 is its atomic mass. 17 is its atomic number. You can do in your head. You might want to pause this, see if you can figure it out. Hopefully, if you paused it and tried it yourself, you came up with following numbers. There's your atomic number. So that's 17 protons, 17 electrons. And then to figure out how many neutrons, you subtract 17 from 36. Okay, and now the last one, and I don't know if I expect you to, unless you've had me for anatomy or some other science that's talked about, I threw an ion in there. We'll talk about ions later, so if you don't get this one right, it's okay. I just wanted to throw it in there. But this has got a superscript of 2 plus. Okay, so this is telling you the atomic mass. This is telling you the atomic number. And in this case, all right, 30 tells you the number of protons. And then you still subtract the 30 from the 68 to get the number of neutrons. But when it's an ion, it affects its electron count. Since this has a positive 2, okay, that means it's got, when you're comparing the electron charge to the proton charge, it actually has extra positive compared to the negative charge. Now, protons are going to stay in the nucleus, and we'll talk about this later. Ions, it all has to do with the electrons, either leaving the atom or some extra ones coming into the atom. Since this has a positive charge, it means we've lost some of those electrons. How many we lose is denoted by the number. So anyway, you remember we said if it's a stable neutral atom, then you'll have the same number of protons as electrons. But if you end up with an ion like this, and it's positive, look how we've subtracted 2 electrons from the total. In a stable one or a neutral one, you would have had 30 here too. Anyway, this is an ion. We'll talk more about that later. I don't want to confuse you right now. All right, our checks for understanding. Here we got a table. We got 4 different elements. It gives you the proton count, neutron count, electron count, which one represents an atom of calcium. In this case, you would need the periodic table. And you would look up, probably the easiest thing for this is just look up the atomic number. So find calcium. Our atomic number is 20. And then you would also need to look at the atomic mass, which is 40. So we know in a neutral stable atom, the protons and the electrons are the same. So they're going to be both 20. And we said that the mass is 40. So in order to figure out the neutron count, remember we take the mass, which is 40, and subtract the number, which is 20. So 40 minus 20 gives you 20. So that's neutron count too. So they're all 20. Proton counts 20, neutron counts 20, electron counts 20. Okay, so for this one, the answer was letter A, the element number 1. Which element has 16 neutrons, 15 protons, and 15 electrons? Hopefully, if you have your period, you're going to have to get a periodic table, print one out, whatever, but you really kind of need one. This makes it easier if it's sitting on the table next to you. Which element has 16 neutrons, 15 protons, and 15 electrons? The easiest way to do this, again, is to look for the atomic number, which again is the proton count. So 15 is your atomic number. You're going to find which element in the periodic table has 15 as their atomic number. And in this case, it's phosphorus. So letter B is the correct answer for that. All right, when compared to sulfur 32 and sulfur 34. Now, I told you when you are dealing with isotopes, you need to write out the word followed by its atomic mass so people know which isotope you're referring to. So we're comparing two isotopes. Okay, and how do we say isotopes differ? We said it has to do with neutrons. So the answer to that one is letter B. When compared to sulfur 32, sulfur 34 has more neutrons. All right, guys, so this is the end of section 2 notes. It was a little lengthy. I apologize for that, but hopefully, you understand what's going on. If not, if you have questions, make sure you ask. Have a great day.